Welcome to Q News Deep Dive. Today, we're diving deep. We're looking right into the tiny hardware that a lot of people think is the future of computing. Superconducting qubits.
Yeah, they're definitely a front runner, maybe the front runner, in this whole race to build a real quantum computer.
Absolutely. And our source material today, it's this really dense technical review, packed with detail. But our job, our mission here, is to pull out the key stuff for you.
Right. Make it understandable.
Exactly. Extract the most important insights, especially if you're maybe newer to this field, so you can really get a handle on where things stand, because it moves incredibly fast.
It really does. And one of the first things the review highlights, which is fascinating, is that the community isn't just on one path. There's sort of two major tracks they're pursuing at the same time.
Two tracks.
Yeah. First, there's let's call it the ultimate dream. Fault-tolerant quantum computers. Big error-corrected machines.
The ones that can run basically anything super precisely for a long time. The sci-fi goal.
Exactly. That's the long game. But then there's the here and now. Track 2 is NISQ.
NISQ, Noisy Intermediate Scale Quantum. We hear that acronym a lot.
We do. And it's about using the qubits we have today. They're noisy. They make errors.
Imperfect.
Totally imperfect.
Yeah.
But you tailor them for very specific problems, specific simulations or algorithms. The idea is to get quantum advantage now with what we've got.
Okay, so two approaches, but underlying both, the building block is the same, right? The superconducting qubit. What is it, fundamentally?
Right, so forget particles for a second. The review defines it really well. It's an engineered thing, a collective quantum excitation. Basically, a specific energy state in a circuit made of superconducting materials. We're building quantum mechanics onto a chip.
Okay, let's get into that hardware then, the foundation.
The absolute heart of most of these is the Josephson junction. Tiny component, huge impact.
What is it physically?
It's simple, really. Two superconducting bits of metal separated by a really, really thin insulating layer, like nanometers thin.
Yep.
And the magic is that pairs of electrons, Cooper pairs, can tunnel across that insulator coherently.
Meaning they keep their quantum state. And no energy loss.
Exactly. Lossless tunneling. And what that gives you, electrically, is a nonlinear inductor. And that nonlinearity, that's everything.
Why? What does nonlinear get us here?
Well, think about a standard electrical circuit. Quantum mechanically, it acts like a quantum harmonic oscillator, a QHO.
Okay.
The energy levels in a QHO are perfectly evenly spaced, like rungs on a ladder, all the same distance apart.
Right.
So if you zap it with microwaves to go from the ground state, state 0, to the first excited state, state 1.
Which is what you need for a qubit, 0 and 1.
Precisely. But because all the energy gaps are the same, you might accidentally keep going up to state 2 or state 3, leakage. You can't reliably just pick out the 0 and 1 states.
I see. So you can't isolate the two levels you need.
Exactly. You need a harmonicity.
Yeah.
You need the energy gaps to be different. The gap between 0 and 1 needs to be unique, different from the gap between 1 and 2.
And the Josephson junction creates that difference.
Yes. That nonlinearity it introduces changes the energy landscape. It makes the steps on the ladder uneven. So now you can tune your microwave pulse precisely to only drive the 0 to 1 transition. You get control.
Makes sense. So that junction is key to making a controllable qubit.
Absolutely fundamental. And the journey to figure this out was quick. The first design, the charged qubit or Cooper pair box, it worked. Showed quantum effects.
What?
But it was super sensitive to stray electrical charges in its environment. Charge noise. Made it hard to build reliably, and the quantum state didn't last long. Poor coherence.
So what was the breakthrough?
The transbond qubit is basically a clever tweak on the charged qubit. They added a large capacitor in parallel, shunting it.
Okay, shunt capacitor. Why did that help?
It pushes the qubit into a different operating regime. Technically, where the Josephson energy, EJRI, is much bigger than the charging energy, like 50 times bigger or more.
And the effect?
It makes the qubit exponentially insensitive to that charge noise that plagued the earlier designs. It's kind of ironic. A charged qubit designed to ignore charge.
Ah, okay. And that worked.
It worked brilliantly. Reproducibility shot up. Coherence times jumped dramatically. We're talking 50, even 100 microseconds now. That stability is why the transbond is, the go-to qubit for most gate-based systems today.
And with better stability comes better control, presumably.
Oh, yeah. Single qubit gate fidelities, how accurately you can flip the qubit state, are routinely over 99%, often much higher.
How do they get that precise?
Sophisticated control pulses. The review mentions techniques like DRAG derivative removal by adiabatic gate.
DRAG. What's that doing?
Basically, when you send a pulse to flip the qubit, it's not perfectly clean. It can slightly excite those higher energy levels you wanted to avoid, the two-state and so on. Leakage again.
Right.
DRAG cleverly shapes the microwave pulse. It adds a second, related signal that effectively cancels out the pathways leading to those unwanted higher states. It keeps the qubit locked into just the 0 and 1 space.
Very clever engineering. Okay, so this high-fidelity, stable transmon, that really paved the way for the NISQ era, right? Doing useful things, even with noise.
Absolutely. Once you have a decent building block, even if it's not perfect, you ask, what can we actually build? What can we compute?
And the big headline there was Google's quantum supremacy experiment.
Yeah, that was a huge moment. Sycamore processor, 53 qubits.
What was the task? It wasn't solving a real-world problem, was it?
No, not directly. It was a carefully constructed benchmark problem, sampling the output of a pseudorandom quantum circuit, basically running a complex quantum process and measuring the outcome distribution.
Designed to be hard for classical computers.
Extremely hard.
Yeah.
And they did it. The quantum computer took about 200 seconds.
And for a classical supercomputer.
The estimate was, well, initially thousands of years, later revised, but still orders of magnitude slower, like 3 to 9 orders of magnitude difference. It proved a quantum processor could do something fundamentally faster.
That really kicked things into high gear. And you mentioned Access earlier, IBM putting quantum computers on the cloud in 2016. That seems crucial too.
Totally. It opened the doors. Researchers, algorithm developers who didn't have multi-million-dollar physics labs could suddenly experiment, test ideas on real hardware. Huge accelerator for NISQ.
So beyond that supremacy benchmark, what are the actual NISQ applications people are running now?
2 main areas really stand out in the review. First, quantum simulation.
Using quantum computers to simulate other quantum systems.
Exactly. It's what they're naturally good at.
Yeah.
Simulating molecules, materials, things like the Fermi-Hubbard model, which is important in condensed matter physics, or even processes in biology like energy transport in photosynthesis.
How do they do that? Gates or?
Both ways. You can do it digitally, breaking down the simulation into quantum gates, or sometimes analog simulation where you tune the qubit interactions to directly mimic the system you're studying.
Okay, simulation. What's the second area?
Quantum chemistry and especially hybrid algorithms. The big one here is VQE, the variational quantum eigensolver.
Variational. That sounds like it involves optimization.
It does. And it's hybrid because it cleverly splits the work. The classical computer does the heavy lifting, the optimization part. It prepares some parameters.
And the quantum computer.
It does what it's best at, preparing a specific quantum state based on those parameters and then measuring it. You feed the measurement result back to the classical computer, it adjusts the parameters, and you repeat. Loop back and forth.
Ah, so you use the quantum processor for the hard quantum part, but lean on classical for the rest. Smart way to handle noisy qubits.
Very smart. And it's shown promise. The review mentions calculating the ground state energy for small molecules like hydrogen, H2, lithium hydride, LiH, even BH2, using up to 6 qubits. It's early days, but it shows the potential.
Before we get to scaling up and fixing errors, there's this other approach people talk about, quantum annealing. How does that fit in?
All right, it's a different paradigm. Still uses superconducting circuits, but a different type, usually flux qubits.
Not transpons.
Generally not, no. Flux qubits are often better suited for annealing. And instead of running gates, annealing works by preparing the qubits in an easy-to-find ground state and then slowly changing the system's parameters, the Hamiltonian. So it evolves towards the ground state of the problem you want to solve.
Letting it settle into the answer using quantum effects.
Kinda, yeah. Using quantum tunneling to explore the energy landscape and find the lowest point, which represents the solution. D-Wave is the big company here.
And what problems is annealing good for?
Primarily optimization problems, things that can be mapped onto finding the ground state of something called the Ising model. Think logistics, scheduling, also simulating things like magnetic materials.
So transmons for gates, flux qubits often for annealing, different tools for different jobs.
Pretty much. Annealers often prioritize massive connectivity between qubits over super long coherence times, whereas gate-based machines need that high coherence for sequences of operations.
Okay, that clarifies the landscape. But for that fault-tolerant dream machine, the gate-based one, errors are the killer. Which brings us to quantum error correction, QEC.
The unavoidable challenge.
Well,
If you want to run long, complex algorithms, you have to deal with errors. Physical qubits will always have some error rate.
So QEC is about building robustness.
Exactly. You encode the information of one ideal, perfect, logical qubit across many physical, noisy qubits. Redundancy.
Like RAID for hard drives, but quantum.
Sort of. The core idea is similar. Use redundancy to detect and correct errors.
How do you detect an error without, measuring the data and collapsing the quantum state?
The clever part. You use parity measurements or syndrome measurements. You don't measure the data qubits directly.
Okay.
You use extra qubits called ancilla qubits. You entangle an ancilla with a small group of data qubits in a specific way. Then you measure the ancilla.
And the ancilla tells you?
It tells you about the collective state, the parity of the data qubits it's linked to. For example, it might tell you if an even or odd number of them have flipped, a bit flip error, or if their phase relationship is wrong, a phase flip error. Crucially, it reveals the error syndrome without revealing the actual data state.
Got it. You learn about the error, not the data itself. Then you can correct it.
Precisely. And the way you arrange these qubits in parity checks, that's the error-correcting code. The leading candidate right now is the surface code.
Why the surface code? What's special about it?
Two main things make it attractive. First, its error threshold is relatively high, maybe around 1%, meaning your physical qubits can be somewhat noisy, and the code can still work.
Tolerant?
Yes. And second, it only requires measurements involving nearby qubits. Nearest neighbor interactions on a 2D grid, essentially. That's much easier to physically build on a chip than codes requiring long-range connections.
Makes sense from an engineering perspective. Has it been demonstrated?
In small pieces, yes. The review mentions work by Kelly and others, showing a 9-qubit repetition code, a simple form of error correction, where they could detect errors and demonstrate that the encoded logical state actually lasted longer with error detection turned on. Proof of principle.
Okay, but encoding one logical qubit takes many physical ones. This sounds like it needs a lot of qubits.
It does. Thousands, maybe millions for a truly fault-tolerant machine, which is why people are also exploring fundamentally different ways to encode information, like bosonic encoded qubits.
Bosonic? How's that different?
Totally different approach. Instead of using many two-level systems, like transbonds, you use the many energy levels available in a single superconducting cavity, which is actually a high-quality quantum harmonic oscillator.
Wait, the thing we said was bad earlier because its levels were evenly spaced?
Yeah, the irony. But here, you use clever encoding schemes within those many levels, things called cat codes or binomial codes. You store the logical 0 and 1 states in complex patterns of photons within that single cavity.
Okay, that's a mind bender. What's the advantage?
Potential for much better lifetimes and maybe simpler error correction for certain types of errors. And they've hit a huge milestone, the break-even point.
Break-even, meaning?
Meaning the error-corrected logical qubit lifetime, T11 Alder C, is demonstrably longer than the lifetime of the underlying physical components. Keown and Redfund. The error correction isn't just fixing things, it's actively making the quantum information last longer than it naturally would.
Wow. Okay, that is a big deal. It proves QEC can actually win against physical decay.
It's a massive validation for the whole concept of fault tolerance.
So summing up, we have really high-fidelity gates on transbonds. We've seen NISQ machines do things classical computers can't. And we have proof of principle for error correction, even hitting break-even with these bosonic codes. Progress is amazing.
It really is.
That's the final section, scaling up, going from, say, 20 qubits to 50, then 100, then thousands. The review says this is where the really hard engineering challenges lie.
Yeah, it's not just a matter of stamping out more qubits.
Yeah.
As you scale, new problems emerge or old ones get much harder. The review points to several key bottlenecks.
Like what?
Well, first, just maintaining that high coherence and control across a much larger, more complex chip. More qubits means more potential noise sources, more unwanted crosstalk.
Keeping everything pristine gets harder.
Much harder. Second, calibration. Tuning up a handful of qubits is one thing. Tuning up hundreds or thousands with all their complex interactions, the number of parameters explodes. You need automated, scalable calibration software that we're still developing.
Right. And how do you even check if it's working right when it gets that big?
That's the third challenge, verification. The standard ways we benchmark small quantum processors, like randomized benchmarking, they just become computationally impossible for large systems. We need new, efficient ways to verify performance.
Okay, coherence, calibration, verification. What else?
The fourth big one is connectivity. Especially for codes like the surface code, you need qubits to talk to their neighbors reliably. But as chips get bigger, and maybe need 3D integration for wiring, Ensuring high-fidelity connections everywhere without introducing new problems is a major hurdle. Non-planar connectivity is tough.
So it's a whole stack of interconnected challenges. Getting beyond, say, 1,000 qubits, the review suggests that won't just be incremental improvements, it might need breakthroughs.
Yeah, like potentially moving control electronics right into the cryogenic environment, the dilution refrigerator next to the qubits. Massive engineering challenges there.
Which brings us to a final thought. Given these challenges, is sticking with the transmon the only way?
That's the provocative question the source leaves us with. Transmons dominate now, but are they the best path to massive scale? Maybe not exclusively.
Alternatives?
Alternatives like the fluxonium qubit. It's more complex to build and control, but the review notes it offers potentially much longer coherence times, over 100 microseconds routinely. That could be a huge advantage if gate fidelity is the ultimate bottleneck.
So, better coherence, but harder to handle.
Right. Or maybe hybrid systems using different types of Josephson junctions, maybe superconductor, semiconductor ones, which could offer different control methods like voltage control. The optimal path might depend on whether improving qubit quality or managing complex connections turns out to be the harder problem in the long run. The jury's still out.
A fascinating point. The architecture of the future might look quite different from today's frontrunner. Well, hopefully you listening now feel much better informed about where superconducting quantum computing is today, the amazing hardware, the NISQ achievements, the error correction path, and the big challenges ahead. Thank you for watching today. This was QNews Deep Dive.